Hey guys, welcome back to AP Physics C. Today we are going to be focusing on vectors in several different ways. We're going to be learning some new vector notation that's going to make this course a lot easier. We're going to be working on vector addition using that new notation, and then we're also going to work on some unit vectors. And it's going to be a great time. Now, it is really important that you do actually watch this one or read the book if you really don't want to watch this one. But the vector notations are going to be super different for this course than anything you've probably been used to before. And it's going to become super important later on when we start doing dot products and cross products that you're using the correct notation. Otherwise, you're going to be getting really lost in the details because things are going to be a little bit weird mathematically later on. So make sure you actually watch this video, learn to use the notation that I use here, and it's going to help you out a lot when we get to two-dimensional motion, which is coming right up. All right, guys, we're starting off with vector notation. Now, in your textbook, vector notation, as I'm talking about it, is actually section 1.9. I know that your reading says to do 1.7, 1.8, and 1.9. 1.7 and 1.8 are vector addition and finding components of vectors, and both of those we can do using this new notation. So I'm going to teach you the notation first, that way we can use it on the other two sections. So section 1.9 is about unit vectors. Now, the word unit simply means one. And what a unit vector is it's a vector with a length of 1. Now that is a very broad definition. You could have a vector in any direction with a length of 1, and that is a unit vector. However, there are two unit vectors that we are going to be working with the most. 3 if we start doing three-dimensional motion, but we're just about to be doing 2, so we're only really going to be working with 2 for a minute. So in an XY plane, like this, typically you define a positive and a negative for each, and you write your vectors as either a length with an angle, or you break them down into components. Like if this was a force, you would say force in the x direction and for equals something, and force in the y direction equals something else. Okay, that's typically how you would notate this, and you have to do 2 sets of equations for the one for the x and one for the y. Okay, you're having to work out all of those things separately. Well, the unit vector system fixes that so that we only have to be working with one equation at a time and not split it into all of that different math, or all of those different sets of math. And it does that using unit vectors. So there's 2 very specific unit vectors. One pointing in the x direction with a length of 1. So I need to mark that off. This is 1. And then another unit vector pointing in the y direction that is length of 1. Hence, it's a unit vector. So it ends there at 1. So those are the 2 important unit vectors. If we wanted to generalize this into three-dimensional, you could also have one in the z direction. However, right at this moment, we're just going to stick to 2 directions. Sorry, I'm erasing part of my axes there. So those 2 unit vectors are notated a little bit differently than a regular vector. A regular vector we notate with an arrow. However, a unit vector we notate with what's called a hat. And it looks like a little carrot top that is above the letter. So x hat is a unit vector, whereas x with an arrow would just be a vector. Y hat is the y unit vector, whereas y with an arrow would just be some other regular vector. So arrow is just a vector, hat is a unit vector. So what this means is that we can take any vector and write it in terms of those 2 things. We'll see that here in a minute. But before I go on, there are 2 other special names for these unit vectors. Okay. Well, and I'll go ahead and set up a chart that has all three of them, just because you'll see them later. So there's an x direction, there's a y direction. If we were going three-dimensional, there would also be a z direction. And you can have a unit vector going in the positive direction for each of them. However, they are also sometimes notated, and actually I'll probably use this a fair amount myself, as I hat, j hat, and k hat. So the x's, or x and I go together, y and j go together, z and k go together. You can write the x unit vector as I, the y unit vector as j, and the z unit vector as k. Why we made this notation? Not 100% sure. Maybe it's that it gets confusing when you're dealing with x, y, and z inside the equation, plus having the unit vectors there as well. I, j, and k just made it a little bit different. But you need to be able to use both notations, because you'll see them in the book, you'll see them on the AP test, you'll see them anywhere you do physics. So let's go ahead and do an example with these using my super straight axes that I'm drawing here. I'm going to give you a vector. I'm going to make it in the third quadrant, because that's where we're most uncomfy in vectors a lot of the time. We're very used to first quadrant vectors. Third quadrant vectors, not quite so much. So this one is going to be at -4, 3. We see it there. Excuse me, that's -4, -3. Good job, self. And say that was like, that vector was referring to a velocity. Now, if we wanted to do kinematics equations with this, to say finding the displacement, finding the acceleration, something like that, typically what we would do is we would split this, and we would say this is a -3 and this is a 4. So this is velocity in the x direction, this is velocity in the y direction. And then we would set up two different sets of equations, one for x, one for y, figuring out all of that crap. But you don't have to do it that way. You can do this in terms of unit vectors. So you could say this velocity is equal to -4 times the x unit vector minus or plus -3 times the y unit vector. And the reason that works is, well, if you do the negative of a vector, it just flips it around. But this would be 4 x direction unit vectors right there, because each one's worth 1, and then 3 y ones going the opposite direction, going down. So we can just say that vector is what you would get if you added up together 4 flipped x unit vectors and 3 flipped y unit vectors. That's what you would get if you did that. So we can write this in terms of those things. And we'll see, once we get to two-dimensional motion, you can use this equation within all of your kinematics equations, within your definitions of acceleration, velocity, position, all of those things. You can use this notation, and you can keep all of your work nice and simple in one set of equations, rather than having to branch off into an x set and a y set. And this is going to apply to forces. This is going to apply to so many different things. It keeps it nice and simple. There are other ways to notate this as well. I showed you guys earlier that you could do this as -4 I for x minus 3j for y. That's one way to do it. That's actually the notation that the book uses. And then there is a final way that is, I've seen it both as parentheses and as like brackets. You could say this would be -4, -3, 0, where this is the x, the y, and the z, or you could have it as -4, 3, sorry, those are -3s, 0 with parentheses. I've seen it both as brackets and as parentheses. Now the brackets here do mean something different when you get to like upper level quantum mechanics, if you ever decide to do physics to that extent. So I would maybe recommend the parentheses option because the brackets mean something different. However, I do catch myself using the brackets more often than the parentheses. And you could also shorten this notation to just end here or end there, since we're only doing x and y right now, but when there's 3 of them, it's x, y, z. And you can use whichever of those notations works best for you. I'll be sticking a lot of times with this one and this one. So now we're actually going to move over to section 1.8, which is components of vectors. So I do not understand why on earth they did this, but the book puts adding vectors before it puts components of vectors. So this is section 1.8. You can't really add vectors without using their components unless they are perpendicular or parallel. But anyways, it just blows my mind. So we're going to do components of vectors first, and then I'm going to do addition of vectors. So we're in section 1.8 right now. So vectors have components. We know this. We just looked at them. On a coordinate grid, coordinate axes, whatever, you'll have a vector. We'll make a nice comfy quadrant 1 on this time. And that vector is usually at some angle theta. Occasionally it'll be an angle phi or phi. That was a really bad phi, phi, whatever. Let me draw a better one. Occasionally you'll have that if you're in 3 dimensions on your vector as well. But the vector will have components in the x and y directions, or the x, y, and z directions if you're in 3 dimensions. So this one down here is the x, this one here is the y, and then this would be your vector. Now these always form right triangles because we are using what's called an orthogonal coordinate system. Orthogonal basically just means right angles. So our entire coordinate system is going to be at right angles to each other. There are some non-orthogonal coordinate systems out there, but we will definitely never deal with those. So since our components form right angles, this makes a right triangle, which is great because we can just do a right triangle trig on it. And I'm sure you guys know how to do that. So your y is going to be, or your y component is the hypotenuse, or your total vector, times the sine of the theta, and your x is your vector times the cosine of the theta, because adjacent and opposite. You guys know how to do that stuff, or if you're a little bit rusty, hopefully you at least can think your way through practicing that a little bit. So if we wanted to write that with new notation, what we would get is the velocity vector equals the x, which is the velocity vector times the cosine of theta. And actually, my notation here is kind of really sloppy. What I should have is just v to indicate the magnitude, because I'm not doing the whole vector, because that's actually a really like a bad thing. Anyways, so I'm just doing the magnitude. That's the v without the arrow. That's the magnitude, or the length of that vector. So I'm doing v times cosine theta in the x direction, which we'll notate as I, plus v times sine theta in the y direction, which I'll notate as j. Okay, so this is a generic vector. I could plug in the length for the v and the angle for the theta, and then I would have my actual vector. And all you got to do is find those components using right triangle trig. You also got to be careful about signs, because if you do your theta from the horizontal, you're going to have to handle, you're going to get the same stuff, but you're going to have to handle the positives and negatives yourself. Those aren't going to work out mathematically if you measure the angle from there. If you measure the angle from a vertical, like so, your sine and cosine are going to switch. But in general, when talking about vectors, the standard practice is not to measure your angle from anywhere besides the positive x-axis. So if I have a third quadrant vector over here, standard practice is to actually call my angle that whole thing there. And if you do that, all of your positives and negatives work out. You get the right components. Everything is great. If that's not comfortable for you, you can measure it from wherever you like. Just make sure that you're using the trig functions that are appropriate and including signs as necessary. Something that is not super apparent and that I actually did a bad job of here on my notation because I was being sloppy. Let me fix it. Is that components themselves are not vectors. Components are straight up just numbers. Okay, numbers all by their lonesome. They do not have a direction included in them as like a mathematical entity. They are just straight up numbers. Okay, and then the last thing with components of vectors are a couple of formulas. And actually, these turn out to be pretty cool. Let me move some stuff around so that we can... Oh, I can't move that because it moves my title too. Okay, well, I'll just do this stuff over here. So one thing you need to be able to do with vectors is figure out their magnitude. Obviously, you do that using Pythagorean theorem. I cannot talk while I spell Pythagorean. Which we all know to be a squared plus b squared equals c squared. And that tells you the length of your vector. Now, if you look at that with our vector notation here, it turns out kind of cool. And actually, I'm going to have to go on to a new slide to do that. So our generic notation was that a vector equals the magnitude of the vector times, let's see, it was cosine theta in the x direction, which is I hat, plus magnitude of the vector times sine of theta in the y direction, which is j hat. And we could also notate that if we wanted to as, I'm going to use the brackets, as v cosine theta, comma v sine theta. And I'm not doing the z direction, but it would just be a zero tacked on there to the end. So if we want to know the length of that, to do Pythagorean theorem, we just have to square all of the components and take the square root. Even if there's three components, even if it's 3 dimensions, you still just square everything and then take the square root. If you want to mathematically prove that, go for it. You know, it's kind of interesting. It's not a hard proof. It's a little trivial. If you want to try it and you can't figure it out, let me know and I'll come show it to you. But anyway, so we're going to do Pythagorean theorem on this. And our two components are v cosine theta and v sine theta. So I'm going to square those. V cosine theta squared is v squared cosine squared theta plus, and then it's going to be v squared sine squared theta. Easy peasy. Take the square root. Now, if you look at that and you're not familiar with trig, you probably think, ew, gross, nasty, disgusting. But let's do a little bit of factoring here. We can factor out the v squared, so we get v squared times cosine squared theta plus sine squared theta. And then we can take the square root of each of those parts separately. Square root of v squared, and then square root of cosine squared theta plus sine squared theta. Square root of v squared is just v. And if you know your trig identities, cosine squared theta plus sine squared theta equals 1. And the square root of 1 is 1. So we just get v as our magnitude of v. It's nice and easy. So we've just shown that our generic vector notation does in fact work. But anyways, if you needed to find, if you just knew the components numerically, like if you just knew this was a 3, 4 vector, okay, that's 3 in the x direction, 4 in the y direction, then you do all of your Pythagorean theorem. 3 squared is 9, 4 squared is 16, add them together you get 25, take the square root of, and your vector is 5. And you can also find the angle theta if you have those things using inverse tangent. So you've got tangent to the negative first, which is not actually to the negative first, just means inverse, of the opposite over adjacent, which is same thing as inverse tangent of y over x. That'll give you your theta or your angle. So Pythagorean theorem for your magnitude or your length, and this puppy for your angle. And now we move on to our last thing, which is vector addition. Now when I say vector addition is made easy by this notation, I don't really mean that it's any easier than it was, other than the bookkeeping is pretty nice. So when you're doing vector addition, like say you were going to take, this is a really bad coordinate grid. Say you're going to take this vector and this vector and add them together. What you'd have to do is split them into their x and y components. And then you're going to add the x components together, or in this case subtract, because that's a negative x. We'll make this 1 and 1, and this 2 and 2. And then add the y components together, so on and so forth. And usually when you do that, if this is vector A and this is vector B, what you have to do is say here's all my x's, and then you do a sub x equals, let's make this theta and this one phi, is a times the cosine of theta. And then your b x is negative b times the cosine of phi, yada, yada, yada. And your bookkeeping goes that way. Instead, now we have a new way of writing these things. You can say A is equal to the magnitude of A, which you probably know, you just know the length. That's probably what's given, times cosine theta I plus a sine theta j. And you know B is B cosine, well, we're not actually going to do the B cosine because this time, oh, it is cosine, sorry. B cosine theta, not theta, phi. Guys, sorry, it's been a long weekend. And that's I, and that's negative in the negative direction, plus B sine phi j. So that's what we would have written out as our things. If you actually had lengths and angles, you could calculate them. In order to add them up, all you got to do is add them straight up in this notation like this. So A plus B is equal to A cosine theta minus B cosine phi times I plus A sine theta plus B sine phi j. And that's how you would write it. And if you actually had numbers, you could plug all of it in and do it that way. So it allows you to keep both the x and the y in one equation, nice and neat. And then eventually it'll be the x, y, and z all together. Now, right now you might be saying this is just like a super cosmetic thing. I don't understand what the point is. It's not really any different than what we've been doing besides the way we're writing it. Yes, it is the same operation the vector addition is. However, after we get done with kinematics and we start moving on to forces and such, we're going to get into sections 1.10 or section 1.10 of this chapter, and it's going to require this notation because we're going to start doing what's called vector and scalar or cross and dot products, and those have to have this notation. It is 100% necessary. You can't do it any other way besides this notation. So we're going to get used to using this on something that is simple and as easy as vector addition, so that way when we get to the new hard stuff, you'll be nice and used to this notation. Okay, my last little bit before we're basically done with vector methods here is negative vectors. Okay, so if you were gonna, for example, subtract, say a minus b, when you are subtracting or taking the negative of a vector, you simply distribute a negative to all its components. So for example, this one up here, if I wanted to do negative a, it would just be negative a cosine theta I minus a sine theta j. So whenever you do these, and if you're doing subtraction or if you're using a negative vector, you need the flip of a vector, the opposite of a vector, and graphically the negative of a vector is just the continuation of the line out the other side. If you need the negative of a vector, then all you got to do is distribute that negative through. So vector subtraction is basically just vector addition, but you're distributing a negative through your subtracted vector. All right, you guys let me know if you have any questions or if you're struggling to use this notation. That way I can help you out, but it is really necessary later on in the course, so I really hope that you will start using it on all of your work. All right, let me know if you got any questions.